This video is all about vectors, what they are, along with how to use and work with them. This will not be an exhaustive look at vectors, but more simply an overview, to give you what you need at this level in physics. To begin, there are two terms that need to be incorporated into your vocabulary. They are scalar and vector. A scalar is simply a number, with a certain unit associated with it. This is like saying I am 1.8 meters tall, or my bottle holds 1.5 liters of water. These are scalars because they both describe a quantity completely. A vector, on the other hand, is a quantity with an associated direction. These are qualities like velocity, acceleration, and force. When we write down a symbol to represent a vector, we take a letter, like F for force, and put an arrow on top. This is because vectors are represented by arrows when we work with them visually. The numerical, or scalar part of the vector is called the vector's magnitude, and is always positive. The direction is what can make it negative. The magnitude is often represented by either the same letter without an arrow above it, or with vertical lines around the vector. When dealing with vectors in 2 or 3 dimensions, a vector can be broken down into a separate component for each dimension. You might see this in a few different ways, but the most common ways I have seen in physics are with angle brackets surrounding the components, or to write them added together and multiplied by I, j, and k. I'll explain what these mean in just a little bit. Each component corresponds to a different dimension in a Cartesian coordinate system, represented by x, y, and z. If you are unfamiliar with this system, it is simply how we represent space, or possibly some other quality, like velocity or temperature, in a graphical kind of way. If we are only looking at one dimension, we use the x-axis. 2 dimensions use the x and y axes, and 3 dimensions require a third, the z-axis. If we are working in only 1 or 2 dimensions, the other dimensions are implied to be equal to 0, and we don't have to use them. As you can see, the blue vector, called v sub x, is the same horizontal width as the purple vector v. This is partially what it means to be the horizontal, or x component, of a vector. The same is true for the vertical vector in red, named v sub y. Each component of a vector is the distance traveled along that axis, starting at the tail and going towards the tip of the vector. This has the same end effect as the main vector itself, and this is what is meant visually when we talk about vectors numerically. The magnitude, or length, of the vector can be found by applying the Pythagorean Theorem, where the hypotenuse, in this case the magnitude, is the square root of the sum of the squares of the components. You've seen this theorem in 2 dimensions, but it carries to 3 dimensions as well. Before we go on to how vectors can be dealt with mathematically, I want to explain the ijk thing, because you will likely see this at some point in physics. You may see them wearing little hats, and what they represent are the unit vectors in the direction of the x, y, and z axes respectively. Being unit vectors means their magnitude is equal to 1, and since 1 multiplied by anything just gives back that anything, they are simply here to give direction, namely in the x, y, or z direction. This brings us to scalar multiplication. Scalars are called so because when multiplied by a vector, they scale the vector. When a scalar is negative, it scales the vector and flips it in the opposite direction. Component-wise, the scalar is distributed to each part of the vector, scaling each component the same. Adding 2 vectors together can be done visually by placing the tail end of one vector on the tip of the other. The resulting vector is the vector that can be drawn starting from the tail of the first vector and ending at the tip of the second. Looking at the components of the vectors, they are added like this, where each component of one is added to the corresponding component of the other. There are 2 ways vectors can be multiplied. One is the dot or scalar product, which yields a scalar answer. The other is called the cross or vector product, which gives a vector that is perpendicular to both the vectors being multiplied. For now, I will just go over how they can be performed, without a deeper explanation, as that is the most important aspect of them right now. If you are curious about where they come from, I would suggest looking them up. There are many good resources that explain them well. The dot product takes two vectors, multiplies their components, and adds them together, just like this. Mathematically, this is equivalent to finding the magnitudes of the two vectors, multiplying them together, and multiplying this by the cosine of the angle between the two vectors. It does not matter which order the dot product is done in, you will get the same answer. But this is not true of the cross product. The cross product takes two vectors and produces another vector that is perpendicular to the two original vectors. The magnitude of the new vector can be found by multiplying the product of the magnitudes of the first two vectors by the sine of the angle between them. The resultant vector can then be in one of two directions. The actual direction is found using what is called the right-hand rule. To do this, start with your pointer finger in the direction of the first vector. Then point your middle finger in the direction of the second. And the way your thumb is pointing is the direction of the cross product vector. This is why the order of multiplication matters for the cross product. Starting in the direction of the other vector produces a vector in the opposite direction. Some other useful manipulations for vectors include how to find the components that make up a vector starting from the magnitude and an angle, and how to find the unit vector that gives only the direction of the original vector. These are both fairly simple geometric strategies. In order to find the components from the magnitude of a vector, we just use a little trigonometry. If we know the angle the vector makes with the horizontal, we can use the mnemonic SOHCAHTOA that many of you have probably learned from trigonometry class. If you have never heard of this mnemonic before, it just means that the sine of the angle is equal to the opposite side over the hypotenuse. The cosine of the angle is equal to the adjacent side over the hypotenuse, and the tangent of the angle is equal to the opposite side over the adjacent side. Where the adjacent side is the horizontal component, the opposite side is the vertical component, and the hypotenuse is the magnitude of our vector, which makes our trigonometric relationships look like this. So, to find the horizontal component, we just multiply the magnitude times the cosine of the angle, and the vertical component is found by multiplying the magnitude times the sine of the angle. If we know the angle the vector makes with the vertical, the sine and cosines are simply switched. Finally, if it ever comes up that you need to compute the unit vector in the direction of a certain vector, we just find the magnitude of the vector and divide each component by it. This is because dividing anything by itself leaves a value of 1. And since the magnitude is a positive scalar quantity, it doesn't change the vector's direction, and we are left with a vector of length 1 in the direction of the original. This treatment of vectors has not been rigorous, but should be sufficient to begin using them in an effective way. Vectors are useful tools, not something to focus too much on for the purposes of this course. That being said, if something is confusing, I suggest asking questions either in the comments or over on Reddit. Also, doing a little searching on your own is a great way to satisfy a curious itch. I appreciate you taking the time to watch this video. Please like, share, and subscribe to support my channel. And if you feel you are able, and that these videos are worth it, you can support me through Patreon, crypto, or PayPal. Links in the description.